microcontrollers is really fun, isn't it? I just love getting me a new dev board, powering it up, hooking up the signals, and jumping right into the code. We just take this data over here, run it through my handy-dandy algorithms, and put the output over there to control our... shoot. I think I kind of forgot a step there. You see, as much fun as the digital and software part is, we live in an analog world. Just about every MCU project I've ever done has to take the analog signals in and convert them into digital data before we can jump into my favorite part. But that analog part can be tricky. Hi, I'm Amelia Dalton, host of Chalk Talk. Today we'll be chatting with Alexis Alcott of Microchip about a new family of MCUs with intelligent analog. That's right. They've done all the work for you to get rid of pesky noise and clean up. Well, heck, why am I telling you about it? Let's talk to the expert right here. Also, before we get started, remember to click that link. There you can download a free white paper entitled The PIC24 Analog Design Guide. Thank you so much for joining me today, Alexis.
Thanks for having me.
So, Alexis, I'm feeling kind of heartbroken now because the world is, in fact, not just zeros and ones.
It's true. It's an analog world out there.
It is.
The things that we see, hear, and interact with, they're not made of zeros and ones after all.
Yeah.
In order to be successful today, in fact, analog engineers have to be competent in digital design and vice versa.
True.
It's a really different environment out there. Analog designers are having to do digital work, and digital designers are having to do analog work.
Mm-hmm.
And most people aren't having teams of analog engineers and digital engineers to work on those separate parts of designs anymore. So
True.
they're having to combine those efforts.
Alexis, I have worked with a couple of those analog people you mentioned, and they didn't seem quite like the rest of us. Let's talk about those guys in particular.
Sure, we can do that. Yeah, the analog guys, they typically care about precision, noise immunity, sensors, and everything's a variable signal. There's no zeros and ones. It's all somewhere in between, all the shades of gray. A lot of times they're not as comfortable with the processors and the controllers.
Yeah.
So what we try and do is offer them lots of example code to start with.
Nice.
So they never have to start from scratch with a blank page, that scary blank page. They can start with some demo code and just tweak the parameters that they need to.
Okay, what about the digital people? More sensible, maybe a little more OCD, but...
Hey, now, I take offense. I come from the digital background.
Oh, no.
No, it's all about the zeros and ones for those guys. Logic, programming, all that comes very easy. It's the analog stuff that seems a little more like black magic.
True, yeah.
And for these digital-focused engineers, what we're trying to offer with these intelligent analog PIC microcontrollers is all the analog stuff's already on board.
Nice.
So we've debugged a lot of the issues that you'd have to do on the board before. And now all those analog components, it's just like another peripheral. So you can program it, the registers, just like you could a UART or a SPI.
Very cool. But what does this intelligent analog have to do with these groups of engineers?
Since teams are being forced to do more with less, what we're trying to do with these intelligent analog microcontrollers is combine both pieces into one product. Making it easier to wear both those digital and analog hats, if you were.
Yeah, I think I have that hat. Wait a second.
Halloween?
Yes, maybe.
So by combining both the analog and digital, we're hoping that you can save board space, simplify your design, and get to market faster.
Fantastic. And I'm not sure about that EE time story you got there, but that's okay. We'll move right along. Okay, so what does this all mean for me in my design work?
Well, in your design, what you'll be able to do is see that all the analog design was done by Microchip.
Cool. Okay.
So we've debugged all those noise and communications issues for you.
Nice.
And from one platform to the next, you'll get very, very consistent analog performance. And you won't have to start over each time you do a new platform.
Brilliant. Okay.
The integration that you'll see will provide faster data path, lower noise on the system and on the board, smart connections inside the chip, and in the end, you'll get to market faster with a lower cost design.
Fantastic. Everybody loves that.
Yeah, who doesn't mind that?
So it seems to me that most of the MCUs that I've worked with in the past have some kind of analog on them, 10-bit ADCs.
That's true. And these parts are a little bit more than just a 10-bit A to D.
Okay.
So what you'll see are high precision or very high speed A to Ds, things like a 16-bit sigma delta,
Right.
or even a 10-bit A to D or a 12-bit A to D with 10 megasamples per second.
Yeah.
So that's more than what you see on a typical micro.
Sure.
Things like DACs, op amps, and then some more unique integrated peripherals like the charge time measurement unit, which offers a constant current source, or even a zero cross detect that'll help you see when your AC crosses through ground.
Cool.
So some more innovative, unique peripherals are what we are considering these intelligent analog micros.
Gotcha. Okay, Alexis, can we walk through an example of what this means in practical terms?
Sure thing. Right here, you'll see a picture of a PIC24 GA306 microcontroller. And that's a part that's a very popular one for us, but it doesn't have intelligent analog on board.
Yeah, I think I did a chalk talk about this once upon a time.
Yeah. So what you'll see here is the layout of a portable sensor board.
Okay.
It's got a lot of components on it, A to Ds, DACs, USB, op amps, in addition to the microcontroller.
Okay, yeah.
So with a discrete solution, you have to have all of those components on your board. That's going to increase your board size.
For sure, yeah.
Also, the routing complexity is increased because to get your signals back and forth between those chips, you're going to have a signal. In addition, you'll have to shield that signal.
Right.
And then you want to make sure from a board design standpoint, your USB and A to D both are very isolated from each other so you don't have any noise issues.
Yeah.
So the board design here can sometimes take 2, 3, 4 spins to get all those noise issues debugged.
Maybe so, yeah.
In contrast, if you swap that out with a new PIC24 GC family micro that has the intelligent analog on board, you can see right away there's quite a bit of board savings.
Yeah, absolutely.
Much smaller. What you can't see in the picture as much is that because it's all integrated on one chip, the routing becomes so much more easy.
Ah, right.
So all those signals before to the A to Ds, USB, op amps, all that's now inside the chip, making your board design a lot more easy.
Yeah, absolutely. Now, you said we could reduce noise. Let's talk about that.
Yeah, noise reduction. So basically, when you have a discrete analog solution versus an intelligent integrated solution, the intelligent integrated solution is going to give you much easier routing. Fewer traces needed because you don't need to route to all those external components.
Right.
The ones you do need to route to will then be shorter traces. You'll need less shielding. And the overall PCB board size is going to be much smaller. Your system cost ends up being lower.
Yes.
And your time to market, because you need less revisions, quicker.
Perfect. Absolutely wonderful. Okay, so a while back you also mentioned increased throughput. Now, how does that happen?
Sure. So to increase the throughput, basically, if you're looking at a discrete analog solution, typically to get to that external A to D, you're using a SPI or a UART in most cases. Well, that can sometimes be a bottleneck. So by integrating that on board, your bottleneck's eliminated.
Oh, right.
You can read directly from the A to D and use that data immediately. In fact, on some of our products that have DMA, that data is directly transferred into the RAM and you can start your processing immediately.
Okay, it seems like this would be useful in a lot of different scenarios, but what kind of applications are you looking for with this?
There's a couple applications that we're focused on and that we're seeing the most success in so far.
Yeah.
The first is in the portable medical equipment area. So things like glucose meters, pulse ox, or blood pressure cuffs. We're seeing a lot of success there because of the need for high precision analog. You want very precise measurements in medical applications.
Yeah.
And also a lot of these are battery operated. And so you see a benefit with the low power of some of these micros.
Sure.
Another key area is in sensing of different kinds of environmental equipment. So lab instrumentation, environmental quality sensors, even gas sensors.
Cool, okay.
And then the final area that we're really focused on is in the area of power. So because of the high-speed A to Ds and the very tight control loops that these systems enable, these are ideal products for power conversion, power measurement, even LED lighting, battery charging, and things like that.
That makes sense. So you have some specific examples to walk us through, right?
I do. Yes, the first one is a PIC24 being used in a smoke detector.
Okay.
So here what we'll see is at the top part of the block diagram, we've got the low battery detect.
Okay.
So you always want to know when your smoke detector battery is going out.
Absolutely.
And usually at my house, it's around 2 in the morning. And here what you see is the A to D's reference to your VDD or your battery source.
Okay.
And then you're continually measuring that against your internal band gap. That band gap is a constant, so any change in the A to D output value represents a change in your VDD. meaning your battery's dying.
Gotcha. Yeah.
You set a certain threshold or trip point, and once your A to D output goes below that amount, your low battery detect will go off.
Gotcha.
Now, on the bottom left part of the diagram, what you'll see is your actual smoke detection.
Yeah.
So your smoke chamber is going to be connected to multiple op amps on the chip, one doing transmit and one doing receive.
Mm-hmm.
You've got an IR light that the receiver will see when the smoke's detected. And basically what will happen there is the output of the op amp goes into the A to D, transmitting any information about when smoke's detected.
Gotcha. Okay.
Then, most importantly, on the bottom right of the diagram, you see your DAC connected to your beautiful horn to
Right.
alert you to get out of the house or
Right.
do what you must. So that was the smoke detector. The next application that I have for you is a glucose meter.
Cool. Okay.
So we talked about the portable medical space, and glucose meters are a huge area. We're seeing a lot of people trying to reduce the cost in the meters. And the PIC16, this is an 8-bit product with intelligent analog.
Okay.
And the micro is being used for all of the front-end signal conditioning and conversion for the glucose meter.
Okay.
So on the left side there, you'll see the test strip where your glucose sample gets inserted.
Yeah.
And basically it undergoes a chemical reaction and electrons are produced. The current on the test strip changes according to the glucose concentration, depending on the sample. And that current is put into the op amp, which is utilized as a current to voltage converter.
Ah, okay.
You've got an internal 8-bit DAC that's used with the internal fixed voltage reference to supply a voltage bias onto the op amp. And then you've got an output signal that'll be fed to the input of the internal 12-bit A to D for conversion.
Okay.
So together, you've got all the analog integrated on chip to do a fairly basic, low-cost glucose meter.
Yeah, I see. Okay.
Couple other things that you'll see here. The double EEPROM can be used for storage of the output, and the timer can be used in order to measure the different time of day or the day of the week, so you can do all the trending and save off that information on your glucose trends over time.
Cool. Okay.
I've got one more example for you today.
All right.
In the area of blood pressure meters.
Okay.
We actually have a video of the reference design that Microchip's created for this type of demo on our Intelligent Analog promo page. So this example shows a low-cost blood pressure monitor where a lot of the peripherals on the PIC24GC microcontroller are used.
Okay.
This micro has both a very fast 12-bit A to D as well as a 16-bit high-resolution A to D on board.
Okay.
And the cuff pressure signal and oscillation signal are both sampled by that fast 12-bit A to D.
Ah, right.
We're using several of the op amps here configured as a high-pass filter. And the design uses the 10-bit DAC with a buffered output to provide an adjustable DC offset level as the bias for the op amp.
Okay.
If you see the CTMU, that stands for Charge Time Measurement Unit, that module is used both for the touch sensing buttons as well as a constant current source to the pressure sensor that you see up on the blood pressure cuff.
Ah, okay.
So as you squeeze the cuff, it can get more pressure or less pressure, just like at your doctor's office.
Right.
So overall, you'll get a blood pressure reading, hopefully a good one.
Yes.
And that data can be displayed on the LCD. We've got an onboard LCD controller on the part. So that's an easy connection. Or you can save that data off in memory.
Very cool. Okay.
There's a couple other peripherals on the chip that could be used for a fancy blood pressure cuff if you wanted USB connection for power or for data logging.
Sure, yeah.
Or there's PWMs for output signals and the Spire UART for connecting to wireless modules.
Cool. So you guys have a big portfolio of MCUs.
We do.
What products include intelligent analog?
Good question. We've got several product families that fall under the intelligent analog umbrella. In fact, I think there's over 100 of them today.
Wow.
And they all map into different market segments depending on the types of analog peripherals that are integrated.
Okay.
So at the top left, you can see the medical and industrial type of products. And those are some of the examples we just talked through with the GC family and the KM. Over on the right-hand side, you can see some of the DS-PIC products that map into the advanced motor control and digital power space. And then in the bottom two categories, in the lower cost arena, you'll see more of the PIC16s, our 8-bit microcontrollers that map into low-cost LED lighting and motor control applications.
Gotcha. Okay. So, Alexis, do all of those parts have the same amount of analog integration?
Good question. No, in fact, it scales by the complexity of the product.
Ah, okay.
So what you can see here is that at the bottom of the chart, you'll see some of the PIC 16s that we have with fairly low-end A to Ds, but integrated op amps.
Ah, okay.
And then that scales up over into the PIC 24s and DS PICs, all the way up to our flagship product in the PIC 24 GC that has multiple A to Ds and DACs and more analog content than we've ever had on a PIC micro before.
Wow, okay. I think I got it now. Seems like the GC family has the most intelligent analog integration. I want to know more about that one.
Yeah, the GC definitely has the most. So what you'll see is in the analog section of this block diagram, there's a 16-bit sigma delta A to D that has very high dynamic range and high resolution. Some other applications don't need that much resolution, but they just need speed.
Right.
So we've also integrated 10 megasample per second, ultra high speed 12-bit A to D.
Oh, cool. Okay.
And then the analog is rounded out with 10-bit DACs for things like analog control loops and things like op amps for analog control loops, mic preamp, and signal conditioning. And then all of those analog components together are connected with an internal analog connection switch matrix.
Oh, okay.
And that switch matrix allows you more flexibility in connecting different analog outputs to other analog inputs inside the chip.
That makes sense. Okay, Alexis, I think I'm ready to get started. What do I need? You got a starter kit for me?
Of course. Yeah, we've got a low-cost starter kit. It's the PIC24F starter kit for intelligent analog. And right at the middle, you'll see the PIC24 GC microcontroller is the heart of the system. And it's connected at the top. You'll see that very long black header. That's an analog header.
Okay.
And so all of the analog IOs from the GC are connected cleanly up to that header for easy prototyping.
Cool, yeah.
So the board itself has several sensors integrated for touch, light, and temperature. But if there's other sensors that you need in your design, you can plug them into that header and you can be off and running, developing your prototype.
Brilliant, okay.
There's also sample code that comes with the board, so you can use that demo code and just kind of make some adjustments and changes to get your design up and going.
All right, let's wrap up this bad boy. Recap the main points for me if you wouldn't mind.
Sure. So what makes intelligent analog integration so powerful is that we've done the hard stuff for you. We've eliminated the complicated task of debugging noise sources that reduce your signal integrity.
Yes.
We talked about how the intelligent analog removes that bottleneck in communication speed. We're trying to provide consistent analog performance that you can leverage from one platform to the next, saving precious design cycles.
Absolutely.
Through those intelligent connections inside the chip, we're controlling all those analog components by software, making it much easier.
Yeah.
And the end result being smaller board designs, simplified design cycles, and faster time to market.
Fantastic. Well, I think that's all I have time for. Thank you so much for joining me today, Alexis.
Thanks, Amelia.
Before we go, remember to click that link. There you can download a free white paper entitled The PIC24 Analog Design Guide. For Chalk Talk, I'm Amelia Dalton. For more Chalk Talks, check out the on-demand section of eejournal.com.